In this video, I'm going to look at how we can use Python in order to do computations with matrices. I'm going to look at two options. One is to use NumPy and the other is to use SymPy. As we'll see, NumPy is the right choice when we're dealing with measurements or any other situation where our values are approximate. And so we're working with decimals and we want them to be rounded decimals. It also makes sense if just any situation where what your goal is to get outputs that are decimals or rounded decimals. SymPy is the correct choice if what you want is symbolic outputs. So for instance, if you want fractions to stay as fractions or square roots to stay as square roots. All right, so I'm going to start in NumPy. We'll start by importing all of the necessary libraries or whatever we call them. And in order to define these three matrices, I have these on the screen. We'll define them as NumPy arrays. And the syntax is, we've seen this before, but just as a reminder, is that we enter them as a list of lists, and each sublist is one of the rows. So we have each row as a list, put all those in a list inside the np.array command. So I've defined A, B, and C, and I'm going to print them out so that we can look at them. So these are all correct, and notice that even though B was entered as having 3 halves, that got turned to 1.5 because we're working in NumPy. Addition and scalar multiplication work exactly how you would expect them to. To add two matrices, we put a plus sign between them. So we can see that we got what we should get if we add B and C. And to multiply a matrix by a scalar, we use an asterisk. So taking A and multiplying it by the scalar 4, this is what we get. For matrix multiplication, we need to use an @ sign. We'll look later at what happens if we mess that up. But when we multiply using an @ sign, so where B and A can be multiplied B times A, right? Because the number of columns of B is the same as the number of rows of A, we end up with this 2x3 matrix, which you can confirm if you want by hand, is what we should get. All right, with matrix operations, it's always possible that you try to do something that you're not allowed to do. So for instance, we cannot add A and B because they don't have the same number of columns. And if we attempt to do that, we get this error message that it's somewhat cryptic, but it's telling us that the shapes don't match up, right? To add two matrices, they need to have the same number of rows and the same number of columns. So that's good. We want to get error messages when we do something that doesn't make sense. We have to, if we try to multiply A times B in the wrong order, so we can't multiply A times B in this order because the number of columns of A does not match the number of rows of B. And so if we enter this, we get a similarly confusing message, but this is indicating to us that the columns and rows don't match up. So again, this is good. We get an error message. The error that's really scary is matrix multiplication. So if you mistype, if you forget what's going on and you type an asterisk instead of an @ sign to multiply, for instance, B times A, you're going to get a weird error message and you might not realize what it means. The scary thing is if you try to multiply two square matrices using this command. And looking at what happens if we multiply B times C using the asterisk, we can see what's actually going on. So this will let us multiply, but it gives us the wrong answer. So that top left entry of B times C should be 5 times 1 plus 6 times 2, which is 17, not 5. So what's going on? When we use the asterisk, we're telling NumPy to multiply entry-wise. So we're telling it to multiply 5 times 1 to get that 5 in the top left corner, and 6 times 2 to get the 12 in the top right corner, and similarly 7 times 2 to get 14, and 3 halves times 4 to get 6. That's known as a Hadamard product of matrices. It's not something we'll deal with in this course. There's nothing wrong with that. There are situations when that's something you want to do. It's not what we want to do. And so this is the real, I say scary error, because error messages are a good thing. They tell you that Python's misinterpreting what you want, but sometimes you get misinterpreted, right? You use an asterisk instead of an @ sign, and unfortunately it gets interpreted as something different. So it's really important to keep track of this. it's essential that, because we're often working with square matrices, it's essential that you remember to use an @ sign if you're using NumPy to multiply two matrices. So the final operation I want to look at is the inverse of a matrix. Straightforward to do. Just INV parentheses, and here we get the inverse of our matrix B. Now, what if matrix C is not invertible? You can see that the rows and columns are multiples of each other, right? The second row is 2 times the first row, and so it has determinant 0. What's going to happen if we try to take its inverse? It tells us that it's a singular matrix. That is to say, its determinant is 0. So again, this is a nice error message. It tells us what's going on. What if we do something even, I think, kind of less excusable, right? We try to take the inverse of A. It's not even a square matrix. What's it going to tell us? It tells us the last 2 dimensions of the array must be square. NumPy arrays can actually have more than 2 dimensions. We're dealing with matrices, so they only have 2 dimensions. So this is telling us that we don't have a square matrix. So again, a good error message. All right, so that was matrix operations in NumPy. Let's look at matrix operations in SymPy, which again, this is really only something you should do if you want exact answers. When in doubt, NumPy is usually the right choice if you're unsure of what you should choose to do, because it's quicker. It's more efficient to do multiplication and addition using floating point rather than symbolic representations of your numbers. So first we'll import what we need, and we'll define our matrices. Again, I'm using these same matrices. And when I print them out, what you'll see is that the print function doesn't really give you what you want. And so actually, you just want to type the element, right? That in SymPy, this is often the case, that if you want to get it to print out nicely, you actually just you don't want to use the print function. Okay, so right now this is a problem, because if I want this number to be 1.5 instead of 3/2, I should not be in SymPy in the first place, right? I should be using NumPy. I want it to be 3/2. And so this is where I need to use this S command. We've seen this before, where I need to tell it to interpret everything inside this matrix symbolically, right? Because what happened before was it divided 3 by 2 before it tried to make a symbolic matrix, so it was already working with 1.5. And so if I type it this way, and I left this here, I don't think I even used this in the video, but B alt, I just wanted, in case you want to compare things between what happens with B entered this way and what happens when you enter it just without the S command, you can use that. And so now if I look at this matrix B, I get 3/2 there. So addition and scalar multiplication are the same and will work nicely, right? So we get 11/2, which is, we're trying to do symbolic operations. Multiplying A by 4, we get the same thing. Here's where things are tricky. Multiplication in SymPy is the asterisk, which is kind of what it should be, right? So in NumPy, you have to use the @ sign to multiply. In SymPy, you have to use the asterisk. Just be careful. That's what I always say is, if you're, just remember that there's this issue with matrix multiplication in Python. And if you're unsure at all, just check each time, make sure you're using the correct one. To find an inverse, we no longer have a function. It's just I guess it would be a method. It's a built-in thing to be. And so we're going to click this. If we want to find the inverse of B, notice that we get this as fractions, which is not what we got with NumPy. This is good. This is the whole point of using SymPy, right? The whole point of using SymPy is that we want to get symbolic outputs. And so here I can get this inverse as fractions. And if I want to see it as a decimal, in its decimal representations, rounded to some number of digits, here to 4 significant figures, I think I could use this evalf command. And so that will give me 4 significant figures on each fraction represented as a decimal. All right, really quick, the final thing to show is what happens when we try to find inverses of things that aren't invertible. Here, if we try to take a singular matrix, it tells us that the determinant is equal to 0, which is a nice error message. And here, if we try to take the inverse of a non-square matrix, it tells us that a matrix must be square to invert. All right, so we have two possible ways of doing matrix operations in Python. By default, you should be using NumPy, but if you're in a situation when you want fractions or square roots or something like that that you want to remain as symbols, SymPy is a good choice.